Hello everyone, this is part 3 of topic 12, 13, and 14 for exam 4, excuse me. Last time we left off with Taylor polynomials, so here was the example, and we didn't have to worry about preserving patterns of powers and factorials because it was just polynomials. But now we're going to finish off this section with 2 more examples where they are asking us to give the results using summation notation. So if they ask us to use summation notation, then we have to pay attention, as we're going to see, to patterns of powers and factorials. So to begin with, the definition for a Taylor series. Now this is an infinite series now, not just a polynomial. It's that f of x is equal to f of c and then plus f prime of c times the binomial quantity x minus c and plus f double prime of c over 2 factorial times the binomial x minus c as a quantity squared, and then plus f triple prime of c over 3 factorial times x minus c as a quantity cubed, and that goes on forever as an infinite series. So as opposed to a polynomial where we were able to just stop after the third order or the third derivative, here we're asked to give the infinite series. That's why it says summation notation. But the procedure is the same. That is, we start with 2 columns, one with the function and some of its derivatives. So in this case, f of x is e to the 5x. And then we're going to have another column with the function and its derivatives evaluated at the given value of c, which in this case is 0. So it's really a Maclaurin, but we're going to treat it as Taylor. Okay, so some derivatives. F prime of x, derivative of e to the u, so recopy e to the 5x, but then the derivative of the power, and the derivative of 5x is 5, so I'll slide that in front. And then we have the second derivative of double prime of x. Okay, I'll leave a little space for the new coefficient. Derivative of e to the u, again e to the u, so e to the 5x, another factor of 5. But again, because summation notation, you want to preserve 2 things: the powers and any factorials that may arise. And we'll see that in the next example. I don't think we see the factorials come into play here. But concerning the powers, I don't want to rate 25 because I want to preserve the power of that base of 5. So since there's 2 factors of 5, 5 squared. And then f triple prime. Okay, leave a space for the coefficient, derivative of e to the u, so e to the 5x times the derivative of the power, another factor of 5, and again, preserving the powers, we'll write 5 cubed. And you could calculate as many of those as you like, but that should be sufficient. Okay, f of 0, e to the 0, 1, f prime of 0, 5 times e to the 0, so 5, f double prime of 0, 5 squared, e to the 0, so 5 squared, f triple prime of 0, 5 cubed, e to the 0, so 5 cubed, and so on. Okay, so now we'll substitute. And so the function f of x is going to be equal to f of c, so that's 1 plus f prime of c 5 times the binomial x minus c, but c is 0, plus f double prime of c, 5 squared, over 2 factorial, times x minus c, but c again is 0, is a quantity squared, and then plus f triple prime of c, 5 cubed, over 3 factorial, then times x minus c, but again c is 0, is a quantity cubed, and so on. And notice that we could easily predict what the next term is based on the patterns. Obviously it's going to be 5 to the 4th over 4 factorial, x minus 0 as a quantity to the 4th. Now let's get rid of the x minus 0s, just call them x's. So 1 plus 5x plus, give myself a little more space here. Okay, so 1 plus 5x plus 5 squared over 2 factorial times x squared plus 5 cubed over 3 factorial x cubed, and so on. Now summation notation. So remember, with summation notation, we always have to start at 0. You want to look for alternation of signs, but there aren't any. But there's some patterns in terms of the powers of 5 and the factorials and the powers on x. But they seem to all be the same. That is, there's really an x to the first here, and a 1 factorial in its denominator. There's really an x to the 0 here, and a 0 factorial by definition is 1 in the denominator. So the pattern for the powers on x, the powers on 5, and the factorials all follow the natural sequence of 0, 1, 2, 3. So all we have to use is n's. So this would be, let's say, 5 to the nth over n factorial, and then times x to the nth. Okay, so as a final example, same idea, 2 columns, one with the function and its derivatives, another with those evaluated at, in this case, 5. Okay, to differentiate 1 over x squared, we'll start by rewriting it as x to the negative 2. All right, let's generate some derivatives here. So f prime of x, negative 2, x to the negative 3. We'll get rid of the negative exponents all at once, and after we're done generating a few more derivatives here. Okay, now here we have to pay attention to the fact that if we were to bring down the negative 3 and multiply it by the negative 2, it would give us 6, but consider the fact that 3 times 2 is the start of a product that resembles the factorial of 3. So therefore, I'm going to rewrite this as 3 times 2 times x to the negative 4. And similarly, for the third derivative, instead of multiplying the numbers, again, you want to preserve powers and factorials. And the fact is that that negative 4 swung down makes the new coefficient negative 4 times 3 times 2, which is 4 factorial. So we're going to preserve that, negative 4 times 3 times 2, x to the negative 5th. Okay, let's get rid of the negative exponents. I think I'll move this column over a little bit. Get rid of the negative exponents. Get 1 over x squared, negative 2 over x cubed, 3 times 2 over x to the 4th, and minus 4 times 3 times 2 over x to the 5th. Okay, now evaluate each of those at the given value of c, which was 5. So we get 1 over 5 squared. And I want to leave it like that. I don't want to say 1 over 25 because that's a power. And I want to make sure, again, we preserve powers. So we've got now negative 2 over 5 cubed. And again, you want to leave it like that because you can see the preservation of the powers and the pattern of the powers. F double prime of 5, 3 times 2, we're preserving the factorial. 5 to the 4th, leave it like that. And then finally F triple prime of 5, the negative 4 times 3 times 2 over 5 to the 5th. And we're going to leave that as well. Okay, now you could of course go on with each of those, but that's going to be sufficient because I think we have enough to have established the patterns. Alright, so the definition, once again, I'll recopy it here. And again, don't make this harder than it is, because all it is an exercise in calculating some derivatives, evaluating them at a particular value, and then our definition here for f of x is f of c plus f prime of c times the quantity x minus c plus f double prime of c over 2 factorial x minus c is a quantity squared, then plus f triple prime of c over 3 factorial times x minus c quantity cubed, and that goes on as an infinite series. So then we'll make our substitution. See, all that's happening is the only thing we're doing is going through that process and substituting the values we found for the derivatives in the function evaluated at that point. Also have to pay attention to substituting in the c's as well in the binomial. But the x's stay because the x's define the polynomial. Okay, so f of x is f of c, 1 squared, plus f prime of c, a negative 2 over 5 cubed, and then times x minus c, which is 5. Next term, f double prime, positive 3 times 2 over 5 to the 4th, times x minus c, which is 5, is a quantity squared. And the next term, negative, so triple prime of 5, negative 4 times 3 times 2 over 3 factorial. I'm sorry, mistake here. 3 times 2 over 5 to the 4th was just the coefficient, or the f double prime of c. So we've got 3 times 2 over 5 to the 4th, but then over 2 factorial, because that's part of the definition, the 2 factorial. So the 3 times 2 over the 5 to the 4th, that was the f double prime. Which is just the numerator. And then in the formula, you get the 2 factorial in the denominator. Okay, and then the x minus 5 quantity squared. So then similarly here, we have f triple prime. Here's the minus, and then 4 times 3 times 2 over 5 to the 5th. And then that's divided by 3 factorial. And then the x minus c, which is 5, is a quantity cubed. And that goes on. Okay, but we could actually, in this case, simplify a little bit, because Well, the first two terms we'll leave as they are. 1 over 5 squared and the negative 2 over 5 cubed. That's multiplied by the x minus 5. But then when we consider this term, 3 times 2 over 5 to the fourth times 2 factorial. Let me go off to the side here. Okay, so 3 times 2 over 5 to the fourth divided by 2 factorial. 2 factorial is really 1/2. And so we'd have 3 times 2 over 5 to the fourth. I'm sorry, 2 factorial is not 1/2. And sorry, you didn't see what I was writing there. So I wrote the coefficient here. 3 times 2 over 5 to the fourth over 2 factorial. 2 factorial is really just 2 times 1, or 2. So that's 3 times 2 times 5 to the fourth times the reciprocal of 2, which is 1/2. But then you can cancel out the 2's. Replace them by 1's to be formal. And we just get 3 over 5 to the fourth. So we'll say this is plus 3 over 5 to the fourth now, times the binomial x minus 5 that's being squared. And then similarly, with this term, if we rewrote 4 times 3 times 2 over 5 to the fifth, that's divided by 3 factorial, which is really 3 times 2 times 1. So that's going to be 4 times 3 times 2 over 5 to the fifth times the reciprocal of 3 times 2 times 1, or 1 over 3 times 2 times 1. And now we can notice that the 3's and the 2's both cancel. And so we just get 4 over 5 to the fifth. So this now becomes minus 4 over 5 to the fifth, and then times x minus 5 is quantity cubed. That goes on forever. Plus, it should be not equals there. Okay, so now we're ready for summation notation. So what kind of patterns do we see? So in terms of the summation notation, it's going to be the big sum as then goes from 0 to infinity. Remember, 0 is always the starting point. Notice we do have an alternation of sign, plus, minus, plus, minus. As I've mentioned before, that should be the first thing you look for. So an alternating factor, negative 1. And if the first term is positive, it's negative 1 to the nth, because the 0 in would give negative 1 to the 0, which is positive 1. And if the first term is negative, it would be negative 1 to the n plus 1th. Okay, so that takes care of the alternation of sign. And let's see for the patterns. Let's break it down into 3 things. Coefficients. The numerator is basically what I'm going to talk about. So let's say numerator, because the factorial is kind of separated. The numerator follows 1, 2, 3, and so on. So when we have 1, 2, 3, that's a shift by 1 unit, so n plus 1. So I'm going to write it as a fraction, and we'll have n plus 1 in the numerator. And then let's say the factorial in the denominator follows the pattern of 2, 3, 4, and so on. Okay, now that's a shift by 2 units. So therefore, because when n is 0, it starts at 2. When n is 1, it's 3. When n is 2, it's 4. So it's a shift by 2 units, so it's n plus 2. So therefore, there would be the base of 5 raised to the n plus 2 power. And then we have the powers on x. Or on the binomial quantity, I should say, x minus 5. So let me call that the binomial. And the pattern there is, well, I think it's taking the natural order, right? This is really a 1 here. There's really, if you wanted, an x minus 5 to the 0 in the first term. So it's taking the natural order of 1, 2, 3. And so therefore, we're just going to need n. So x minus 5 to the nth. Okay, so that's the end of topic 12, 13, and 14. And we'll come back when you're ready.